Okay, guys, we are on to the next section, which is heat flow. So, there are three different types of heat transfer due to a temperature difference. One is conduction, second is convection, third is radiation. And these next slides, will show us specifically what that means. Okay, so conduction is kind of like if you were to be at a bonfire or something, and you have I always use like a hanger when I do it. Well, if you get your hand too far up on that metal, so say this is like the metal clothes hanger. If you get your hand up closer here, you start to feel heat, right? So this is just showing that the closer that it is to the fire, obviously at this spot right here, the temperature's way up here. At this spot, the temperature's like, obviously lower. And it just continues to get lower the farther away from the source that it is. Okay, so that's conduction. It's just meaning that it's flowing through the matter, and that the hotter atoms are colliding with the cooler ones. And they're transferring energy, but eventually it sort of runs out, kind of like a wave in a pond or something. If you were to throw a rock into a pond, eventually those waves start to die down. So, okay. Conductivity. So if we go back over here, this was saying that some materials are considered to be really, really good conductors. And then there are poor conductors, which are known as like insulators, like styrofoam, wool, air is even an insulator. You don't see a lot of electricity going through the air. Now, can it? Yes, like lightning, and you can have enough charge that it can jump through the air, but it takes quite a bit of charge in order to do that. So this is showing you the conductivity of different materials. You can see here that the metals, are pretty conductive. Then you go over here to these non-metals, and they get like really little numbers. Like 10 to the negative third that means that it's like 1, 2, 3. So this is the decimal point. So this number is like 0.0013, which is a lot smaller than even 0.11. Styrofoam is in the negative, air, and then vacuums that's just a zero conductivity. Okay, so that was conduction. Convection is another type of heat transfer. So this is energy transfer through the bulk motion of hot material. A good example of this is like one of those old, I think they were called radiator heaters. They don't have these a lot in houses like they used to. But what would happen is they create this heat, and it kind of pushes up through here, and then it kind of sucks back in the cooler air, heats it throughout the system, and then pushes it back out. So it makes kind of this circle. And you've probably heard of convection ovens before. So there's like conventional ovens, and then there's convection ovens. Convection ovens are supposed to be, way better for baking. They can, like I said, they can make this sort of circular heat, which makes everything kind of heat really evenly, and supposed to, really make good cookies and stuff like that. So, natural convection, hot air rises. If you go back to the bonfire situation, that would be like sort of that heat flow from the fire going up, probably from the top of the fire, and then kind of circling back around. Okay, the third kind of heat transfer is radiant energy or radiation. This is energy that's associated with waves. And I don't think it's going to give me a picture, so I'm going to have to bring this up in the book here in a minute. But we'll talk about the electromagnetic waves here in a moment. And this can operate through a vacuum, but the way I always think about radiation is like, if you're at at that bonfire and you kind of hold your hands up, but you're obviously not touching the fire, you can still feel that heat. Those are like waves coming from the heat. Sometimes in the summer you can even see those waves, like if you're grilling or even on the road, you can see those radiant waves. That is waves, and normally we can't see it, but in some situations we're able to. So all objects emit and absorb radiation, and the temperature determines like how much the emission rate is, how much light is given off, things like that. So let me see if I can actually find, of course, my book's not gonna let me, I bet, go. You guys always have to deal with my, my technical difficulties with me. So, sorry about that. Oh, can't really do that, or you guys will see my password, huh? Okay, well, we'll just go back to the, PowerPoint. It's really not that big of a deal. All it was just going to show was kind of like, I can kind of draw it out here actually. You kind of have this line, and over here you've got things like, kind of has these waves, and then they kind of get, this is terrible, they get really, really small. So what that was supposed to do, which I really did poorly at, is it was supposed to have these waves that are really long, and then they start to get smaller and smaller, but sometimes they get bigger, it seems like, on my drawing. It's okay. I always get made fun of for my drawings. All right, so the bigger waves are like your radio waves, you got microwaves, you got your infrared or your UV rays. This is called visible light. This is like your colors, Roy G. Biv, red, orange, yellow, green. All the waves in that little tiny section is the only waves that we can really see with our eyes. Those are the colors. Then over here on this side of the visible light waves is where we start getting into, some of our more dangerous type waves. This is where we end up with like our X-rays and our gamma rays. Okay, so anyway, radiation is a type of wave, but it's, when we think of radiation, we probably think of maybe our brain goes to like cancer patients getting radiation and things like that, which is a form of waves. It's actually, kind of in these gamma rays, which have really, really, really small waves, very high frequency, which are very dangerous. And that's why they do it, because it can kill organic substances. Not only can it kill, like the cancer cells, but that's why you have quite a bit of issues whenever people have to do radiation, because there's a lot of death in even some of the, the good cells. So anyway, that's sort of a view of the electromagnetic spectrum. All right, energy, heat, and molecular theory. So what is this? This is showing us we've got our different phases of matter. And, okay, this is going to show us that energy is going to either be needed or released whenever we change phases. So this is a better picture in my opinion. So you have something like ice, and if you raise the temperature, and remember, 0 degrees Celsius is like freezing. So right at 0 degrees Celsius, what do you think starts to happen to ice? If you're continuing to increase the temperature, it's going to start melting, right? And then it's going to keep on warming, and through this phase right here, we're just at liquid water. But at 100 degrees Celsius, what starts to happen? That's our boiling point. We talked about that with our temperature scales. And so at boiling, we start to go from a liquid to a gas. So these two sections right here, see if I can change my pen color. These two sections right here are our phase change sections. That's where they're going from one thing to another. Okay? And whenever they do that, we have to kind of calculate it a little bit differently. So we've got from a solid to a liquid. We've got this latent heat of fusion, vaporization, sublimation. Sublimation's where it goes directly from a solid to a gas. When it goes from a liquid to a gas, we've got, vaporization, and from a solid to a liquid, we're having like a fusion. So temperature, you've got a melting point, a boiling point, and again, sublimation. Then you have freezing point, condensation point, where it goes back to a liquid, and then sublimation. So what in the world am I talking about? Okay, let's do an example. Actually, I'm just going to stop the video there and get into my book, and then I'll start another video really quick, and it'll be basically another part of this section.